Grounding the transformer enclosure and frame is generally an appropriate practice for safety reasons and to avoid electric shock hazards. However, it is important to note that the ground should not be connected to any of the transformer windings. Connecting the ground to only the transformer enclosure creates a floating ground. This means that the enclosure is connected to the grounding system, but the electrical potential of the enclosure is not fixed to a specific voltage. In the event of a single-phase short, the ground connection to the enclosure will not provide a path for the fault current because the ground is not connected to the windings. Therefore, the fault will remain isolated and will not cause a trip of the primary or secondary breakers. There are several reasons for grounding the enclosure. Firstly, safety. It prevents electric shock hazards by providing a low-resistance path to ground for any fault currents. Secondly, EMI/RFI shielding. Grounds the enclosure to reduce electromagnetic interference and radio frequency interference. Thirdly, lightning protection. Grounds the enclosure to protect it from lightning strikes and surges. Several additional considerations need to be taken into account. Firstly, use a grounding conductor that is sized appropriately for the transformer capacity. Secondly, maintain a low resistance connection between the enclosure and the grounding system. Thirdly, inspect the grounding connections regularly to ensure they are secure and free of corrosion. Based on the information provided, it is acceptable to ground the transformer enclosure and frame, but ensure that the grounds are not connected to any of the transformer windings. This configuration provides safety benefits without compromising the electrical protection of the transformer. The purpose of grounding the transformer enclosure is primarily for safety. It creates a low impedance path for fault currents to return to the source. This low impedance path facilitates the quick operation of overcurrent protective devices like circuit breakers or fuses in the event of a ground fault. By tripping the breaker or blowing the fuse rapidly, the amount of time that the dangerous voltage is present on the enclosure is minimized, significantly reducing the risk of electric shock to personnel who may come into contact with the enclosure. If the enclosure were not properly grounded, a fault current could flow through a person who touches the enclosure, potentially causing serious injury or death. Grounding also helps to reduce the potential for static electricity buildup on the enclosure. Static electricity can create a spark hazard, especially in environments where flammable materials are present. By grounding the enclosure, any static charge that accumulates can safely dissipate to ground, minimizing the risk of ignition. Electromagnetic interference or EMI can disrupt the operation of sensitive electronic equipment. A grounded enclosure acts as a shield, reducing the amount of EMI that can radiate from the transformer and interfere with other devices. Similarly, it can also reduce the amount of external EMI that can affect the transformer's operation. Lightning strikes and voltage surges can damage electrical equipment. Grounding the transformer enclosure provides a path for these surges to ground, helping to protect the transformer and other connected equipment from damage. Now let's talk about the floating ground in a delta-delta transformer system. A floating ground means that there is no direct connection between the transformer windings and the earth grounding system except for the connection to the transformer enclosure. This is a common configuration for delta-delta transformers. One potential issue with a floating ground is that in the event of a ground fault on one of the phases, there may not be enough current flow to trip the overcurrent protection devices, such as circuit breakers, immediately. This is because the fault current path is not as clearly defined as it would be if one of the transformer windings were directly grounded, like in a Y-connected system. However, this doesn't mean it is unsafe. The grounded enclosure still provides a safety path for fault currents. The key is to ensure that the grounding conductor is properly sized and that the connection to the grounding electrode system is robust. Now let's consider a single phase short. With a floating ground configuration, if a single phase shorts to the grounded enclosure, it's important to understand what happens. The fault current will flow from the shorted phase to the enclosure and then through the grounding conductor back to the source. However, because the ground is not tied directly to the windings, the fault current might not be high enough to immediately trip the primary or secondary breakers. It will depend on the impedance of the fault path and the settings of the overcurrent protection devices. This is why it is critical to have a well-designed grounding system and properly coordinated overcurrent protection. A ground fault detection system can be used to detect even small ground fault currents and trip the breakers quickly, even when the fault current is not high enough to activate the standard overcurrent protection. Such a system enhances safety in a floating ground configuration. Now let's discuss some practical considerations for grounding delta-delta transformers. The size of the grounding conductor is crucial. It must be sized according to the relevant electrical codes, such as the National Electrical Code, or NEC, in the United States. The NEC specifies the minimum size of the grounding conductor based on the size of the transformer's overcurrent protection device. For example, NEC Table 250.122 provides guidance on equipment grounding conductor size for alternating current circuits. The grounding conductor should be copper or another approved material and must be properly protected from physical damage. A low resistance connection between the enclosure and the grounding system is essential. This ensures that fault currents can flow easily back to the source, allowing the overcurrent protection devices to operate quickly. The grounding connection should be made with a listed connector that is suitable for grounding purposes. The connection point should be clean and free of corrosion. Regular inspection of the grounding connections is critical. Over time, connections can loosen or corrode, which can increase the resistance of the grounding path. This can compromise the effectiveness of the grounding system and increase the risk of electric shock. Grounding connections should be inspected at least annually, and any loose or corroded connections should be tightened or replaced. Also, consider the environment where the transformer is located. In corrosive environments, special precautions may be needed to protect the grounding connections from corrosion. This might include using corrosion-resistant connectors or applying a protective coating to the connections. Let's talk about the benefits of grounding the enclosure of a delta-delta transformer. Grounding the enclosure provides a low impedance path for fault currents, which helps to quickly trip over current protection devices, reducing the risk of electric shock. Secondly, it helps to minimize the buildup of static electricity in the enclosure, which can reduce the risk of sparks and ignition in hazardous locations. Thirdly, it helps to reduce electromagnetic interference and radio frequency interference, which can protect sensitive electronic equipment from malfunction. Fourthly, it helps to protect the transformer and other connected equipment from damage due to lightning strikes and voltage surges. While grounding the enclosure provides numerous safety benefits, it's important to understand that it does not completely eliminate the risk of electric shock. It is still possible for a person to receive a shock if they come into contact with a live conductor, even if the enclosure is properly grounded. Therefore, it's important to follow safe work practices when working with electrical equipment, such as de-energizing the equipment before working on it, using appropriate personal protective equipment like insulated gloves and safety glasses, and keeping a safe distance from energized equipment. Now let's discuss the use of ground fault circuit interrupters, or GFCIs. GFCIs are designed to detect small ground fault currents and quickly interrupt the circuit. They are commonly used in residential and commercial settings to protect people from electric shock. While GFCIs are not typically used to protect transformers themselves, they can be used to protect equipment that is connected to the transformer's secondary side. For example, if a transformer is supplying power to a receptacle in a wet location, a GFCI receptacle should be used to protect people from electric shock. A floating ground configuration can affect the operation of GFCIs. In a grounded system, a ground fault provides a direct path for current to flow back to the source, which allows the GFCI to quickly detect the fault and trip the circuit. In a floating ground system, the fault current path may not be as clearly defined, which could slow down the response time of the GFCI. However, GFCIs are still effective in floating ground systems, as they are designed to detect even small ground fault currents. To ensure that GFCIs operate properly in a floating ground system, it's important to use GFCIs that are specifically designed for use in such systems. These GFCIs typically have a lower trip threshold and a faster response time than standard GFCIs. In addition to grounding the transformer enclosure, it's also important to ground the transformer core. The core is the magnetic component of the transformer, and it can become energized if it comes into contact with a live conductor. Grounding the core provides a path for fault currents to flow back to the source, which helps to quickly trip over current protection devices. The transformer core should be grounded to the same grounding electrode system as the enclosure. The grounding conductor should be sized according to the relevant electrical codes. The connection between the core and the grounding conductor should be made with a listed connector that is suitable for grounding purposes. It's also important to ground any metallic conduit or enclosures that contain the transformer's primary or secondary conductors. This helps to provide a continuous grounding path throughout the electrical system. The conduit and enclosures should be grounded to the same grounding electrode system as the transformer enclosure and core. The grounding conductor should be sized according to the relevant electrical codes. The connections between the conduit and enclosures and the grounding conductors should be made with listed connectors that are suitable for grounding purposes. Remember that the grounding electrode system is a critical part of the overall grounding system. The grounding electrode system provides a connection to the earth, which helps to stabilize the voltage of the electrical system and provide a path for fault currents to flow back to the source. The grounding electrode system should consist of one or more grounding electrodes that are installed in accordance with the relevant electrical codes. Common types of grounding electrodes include ground rods, ground plates, and concrete encased electrodes. The grounding electrode should be connected together with a grounding electrode conductor, which is sized according to the relevant electrical codes. The grounding electrode conductor should be connected to the transformer enclosure, core, and any metallic conduit or enclosures that contain the transformer's primary or secondary conductors. A properly designed and installed grounding system is essential for the safe and reliable operation of a delta-delta transformer. It helps to protect people from electric shock, minimize the buildup of static electricity, reduce electromagnetic interference, and protect the transformer and other connected equipment from damage due to lightning strikes and voltage surges. When designing and installing a grounding system for a delta-delta transformer, it's important to consult with a qualified electrical engineer or electrician. They can help to ensure that the grounding system meets the requirements of the relevant electrical codes and is properly coordinated with the other components of the electrical system. In summary, grounding the transformer enclosure is an acceptable practice for safety reasons. Make sure that the grounds are not connected to any of the transformer windings. Consider using a ground fault detection system and always consult with a professional.